topic of today's video is going to be solution concentration and how we determine it. So you've already seen an example of concentration of a solute in a solution before. We've actually addressed this as percent mass as a unit of concentration. And as we know, if we want to express a concentration in terms of a percent mass, that would be the mass of the solute, which is the thing that gets dissolved, divided by the total mass of the solution, which is going to be the mass of the solute and the solvent together. Multiply that by 100% and you have a percent by mass concentration. Now, typically in chemistry, we don't use that concentration. The concentration we use most often is a concentration unit called molarity. Molarity is symbolized by a capital M. And the definition of molarity is that it's the moles of solute divided by liters of total solution. And that's important. It's not volume of solvent in the bottom, it's volume of total solution expressed in liters. Now, as a simple example of this, I could make up a 1.5 molar solution of sodium chloride. If I made that up in a total volume of 1 liter, I would need to have 1.5 moles of sodium chloride, and that would be contained in 1 liter total volume of solution. Now, in actual practice, we normally don't make up just a simple liter of solution. We might make up some other volume of solution. So let's say, for example, I want to make up 250 milliliters of total solution. So how would I do the molarity calculation in a case like that? So let's take a look at actually how we would take care of solution preparation in that situation. So here's our job. We want to prepare a 0.25 molar solution of sodium chloride in a total volume of 250 milliliters. Now again, this molarity refers to 0.25 moles of sodium chloride per 1 liter of total solution. Now, to do this, I'm going to need a couple things. I'm going to need first a volumetric flask. You guys have seen volumetric flasks in the lab before. So a volumetric flask looks like this. I'll bring it up close so you can see it. And you'll notice that this particular volumetric flask is actually calibrated to 500 milliliters. So when I actually put my solute and my solvent in here, what we're going to do is mix them up, and then at the end we're going to come to a total volume of 500 milliliters by bringing the level of solution to the mark, which is etched on the neck of the volumetric flask. Now in our particular case, as I mentioned, I want to make a 0.25 molar solution of sodium chloride in 250 mils of total solution. So I would go find first a 250 milliliter volumetric flask, because I know that to make that solution I have to contain a total volume of 250 milliliters. The other thing that I've got to find now is what mass of sodium chloride would be required to prepare that solution. Obviously then I would have to go weigh that mass of sodium chloride out on a balance, and then it would be added to the volumetric flask, some water would be added, the sodium chloride would be dissolved, I would bring the total volume to the mark, and then I would mix the solution carefully at that point. Alright, so let's see if we can figure out how to determine the mass of NaCl that I need. So it's just a dimensional analysis problem. I'm going to start with the 250 milliliters of solution as my given. I'm going to convert that from milliliters to liters, so we can track our units as we go. So milliliters of solution will cancel with milliliters of solution. Then what we're going to do is we're going to multiply by the molarity. Now I'm expressing the molarity based upon its absolute definition, which is 0.25 moles of sodium chloride per 1 liter of solution. What does that do for us? It allows liters of solution now to cancel out. So now I've got the number of moles of sodium chloride that I would need to prepare that solution. All I need now is the formula weight of sodium chloride to get me to the grams of sodium chloride. So moles of NaCl will cancel with moles of NaCl. That's the formula mass of 1 mole of NaCl. And if I do the math here, I find I need 3.6527 grams of sodium chloride. Again, that's going to be limited to 2 sig figs because of the molarity here being limited to 2 sig figs. So I would round that to 3.7 grams of sodium chloride. So as I mentioned, what I would do is I would weigh that amount of sodium chloride out, I'd put it into the appropriately sized volumetric flask. I'd add water, maybe about to the halfway point. I would swirl the flask until all of the sodium chloride is dissolved. Then I would carefully take my level of liquid up to the mark that's etched into the side of the flask, such that the meniscus, or the low point of the mark, just touches, or rather the low point of the liquid just touches the mark on the flask. I would then stopper this, and I would invert it 20 to 50 times to make sure that the solution is properly mixed. At that point, I've got a 0.25 molar solution of sodium chloride in my 250 milliliter volumetric flask. All right, so one other thing that we might find useful when we deal with molarity calculations is molarity can actually be used as a means of calculating moles. All right, so you know, for example, from a stoichiometry perspective, if we're going to actually compare reactants to products or compare anything to anything else in a chemical reaction equation, we know that we have to go through the mole using the mole bridge. Okay, so it's typical in stoichiometry problems where we're given a molar concentration and a volume, and we're expected to now determine moles for a given reactant or product. So in order to do this simple calculation, we need the volume of the solution that we're dealing with in liters, and I also need the molar concentration in moles per liter. Now, as we can see, if we take the volume and multiply it by molarity, we should be able to get to moles. Here's how it works. The volume would be in terms of liters, and if I multiply that by molarity in moles per liters, notice that the liters cancel out, leaving us with moles of the solute. Okay, so it's another way to get to moles, so we can use moles in a stoichiometry problem. So for a simple example, we could ask, how many moles of sodium chloride are found in a 50 milliliter sample of a 1.5 molar solution of sodium chloride? Okay, so I'm trying to get to moles. I've got a volume and I've got a molarity, so we can use those two things to get to moles directly. Now I'm starting out with my 50 milliliters of solution. I'm going to convert that to liters. So I know that in 1 liter of solution, I've got 1,000 milliliters of solution. And now that I've got liters in the top, I can multiply that by molar concentration or molarity. So I've got 1.5 moles of sodium chloride per 1 liter of solution. That's the definition of a 1.5 molar solution of sodium chloride. And when I go through this thing dimensionally, I'm going to get rid of the liters, and I'll find that I'll be left with moles. And if I work this out, I'm going to get 0.075 moles of sodium chloride. Now, that's going to be limited to the 2 sig figs of the moles here. The liters down here are essentially unlimited because of the definition of molarity. Sometimes, however, this might actually be limited to the actual precision of the volumetric flask that you're using. But for our purposes, we're assuming this is 1.5 moles of sodium chloride for exactly 1 liter of solution. All right, so next time when we get back to class, we're going to do one more definition that involves dilution of solutions. So we'll talk about dilution next time, and we'll see you then.